The land of mathematics is an exotic and puzzling place. A strange language is spoken there, with talk of homeomorphisms, differentiable manifolds, and transfinite numbers. But also to be found there are magnificent landscapes, spellbinding ideas, and occasionally, even useful things. So let's take a whirlwind tour of the land of math. You just need a guide, that's me, and a functioning brain, that's you. We're not really going to do any math, just take a look at the countryside. In October 1970, readers of the Mathematical Games column in Scientific American discovered a very unusual game. It plays out on an infinite grid of square cells, each of which can adopt one of two states, populated or unpopulated, live or dead. Its inventor, the mathematician John Conway, presented it as a zero-player game. You played on your own by applying simple rules, through which complex and apparently unpredictable figures are born. You can play with a pencil, an eraser, and a lot of patience. But it's on a computer screen that the game of life takes on its true dimension. At the beginning of the 1970s, it aroused so much enthusiasm that a report by the American Army estimated the cost of wasted calculation time it caused at several $1 million. The game of life belongs to the family of cellular automata. To understand what it's about, we need to go back a few decades. Immediately after the Second World War, the electronic brain was a new idea. Scientists and engineers united around the hope of inventing a new science based on information, cybernetics. The mathematician John von Neumann had just participated in the development of a first functioning computer. He harbored a crazy idea, that of making a model of life using mathematics. And in particular, a model of what, in theory, only living beings are capable, reproduction. What interested him was the theoretical dimension of the problem. Could a machine build a working copy of itself? This thought experiment initially took the form of a floating robot, capable of taking from the surface of the water the various components. But his friend Stanislas Ulam suggested a simpler and more abstract idea, a cellular automaton. A cellular automaton is a simplified world composed of identical cells which possess different states and switch between them in accordance with a set of rules. In such an abstract universe, self-reproduction becomes much easier. For example, if the rule is to copy the contents of the cell 10 paces to the left, you easily obtain a series of identical images. But it was not this type of trivial reproduction which interested John von Neumann. He wanted a reproductive system which was similar to that of living beings. The reproduced object needed to be complex and made up from basic elements, a bit like in nature. The ultimate goal was that variations should be possible to simulate an evolutionary process. It was from this viewpoint that von Neumann reflected upon a complex cellular automaton and managed to prove that self-replication thereby became theoretically possible. He began the writing of a theory of self-reproducing automata, but passed away at the age of 53 without completing it. The book was published posthumously at the end of the 1960s. At this point, it crossed paths with an atypical English mathematician, John Conway. Conway was a jack of all trades. Too ill-disciplined to found a great theory or a school, he nonetheless left his mark on numerous domains of mathematics. While von Neumann participated in the creation of the atomic bomb and the computer, Conway preferred inventing games. His taste was not so much for systems as for solid and handleable things, and experimental mathematics. Far from the image of a solitary mathematician locked away in his ivory tower, he liked discussing with students, playing backgammon, and above all, inventing new games. And that's precisely what he did with von Neumann's ideas. He turned them into a game. A zero-player game, but a game nonetheless, at which Conway and his students played using a Go board or graph paper. After many more complex trials, the rules finally became extremely simple. For each cell, the state of its neighbors at a moment t decide on its state at the moment t plus 1. An unpopulated cell becomes populated if it has exactly 3 populated neighbors. A populated cell continues to be so the following moment if it has 2 or 3 populated neighbors. If it has less, it dies of underpopulation. If it has more, it dies of overpopulation. By applying these two simple rules, very simple objects can generate an astonishing visual complexity. After the article in Scientific American, a fan base grew up around the game of life, which began listing and studying the shapes which appeared. Firstly, come the stable configurations, which Conway called still lifes. There is the pond, the beehive, the loaf, the boat, the snake. There are also the oscillators, which stabilize around a cycle. There is the blinker, the beacon, the clock, the toad, etc. And then there are a few particular shapes which seem to be able to move. The simplest and the most common is the glider, which often appears spontaneously and moves along a diagonal. Such is the complexity of the shapes which appear, that it quickly becomes difficult to follow their evolution by hand. Personal computers, which were beginning to appear at the time, took over the task and made it possible to take the exploration further. But alongside this task of description and classification, which is reminiscent of natural sciences, the game of life can also be regarded from the constructive point of view of an engineer. The majority of starting configurations which Conway studied seemed to end up in a static or cyclic state, and he wondered if shapes could exist which generated an infinite expansion of the population. As he was a gambler, he offered $50 to anybody who could find one or prove that they didn't exist. Bill Gosper, one of his colleagues at MIT, took the prize with this configuration, the glider gun, which, as its name suggests, emits a continuous stream of gliders, opening up a whole new range of possibilities. From this point, Conway and his students were able to construct the equivalent of logic circuits for a computer, transmitting information from one point to another and stocking it in memories. In this way, they proved that the game of life is what is known as a universal Turing machine, meaning that it can carry out all the operations possible on a computer. Over the years, with the progress of machines and algorithms, the enthusiastic game of life community has been able to more and more quickly examine configurations which are more and more extensive, and more complex structures are still being invented today. Someone even ended up programming the game of life, using the game of life itself. Moreover, cellular automata have found numerous applications for modeling physical phenomena like gas diffusion or biological processes like the development of an epidemic. But the dreams of von Neumann and Conway went far beyond questions of calculation. What they hoped to understand, simulate, or even recreate was life itself. With a sufficiently vast, randomly filled grid, explained Conway, all the configurations can effectively show up at one point or another. And amongst these billions of configurations, one might imagine that some might be able to reproduce, and thereby multiply, perhaps evolving, and why not perhaps become intelligent creatures. At the same time, Konrad Zuse, a pioneering German computer scientist, came up with an even more speculative hypothesis. If life can be born in a cellular automaton, might one imagine that our world itself is a simulation, calculated by a cellular automaton or a similar apparatus? For many other scientists, the idea that a form of life could develop within such a simplistic system is proof of a certain naivety. They reiterated that the game of life is purely deterministic, entirely predictable, and that this vision of the world as a gigantic clock had been overtaken by the science of the 20th century, which for its part left considerable space for non-deterministic phenomena. And that's precisely what makes John Conway's invention so fascinating. It seems to straddle these two opposed worlds, and spectacularly illustrates how simple and deterministic rules can give birth to complex and apparently unpredictable phenomena. And what the game of life allows us to affirm with certitude is that an immense, complex, and highly organized universe can be thought up by a bearded creator between two games of backgammon.